Okay, we are going to go over transformations, and specifically we're going to talk about reflections. So a few fill in the blanks here. A transformation is a function that maps a figure, which is the pre-image, onto a new figure called the image. A transformation can change the size, position, or shape of the figure. So by transforming it, basically we're just going to change the picture. This is one of the most basic transformations, which we'll talk about here, but basically the only thing we moved with this one is the location of that triangle. It started over here and ended up over here. Not much changed other than just its location, but that is considered one of our transformations. Okay, so a few key concepts here. I'm going to zoom in really quick here. A reflection. A flip is what we call it. Usually in our daily lives, we would maybe call it a flip. It's a transformation over a line called the line of reflection. Each point of the pre-image and its image are the same distance from the line of the reflection. So something that I talk about with my students is if I'm looking into a mirror, I'm always the same distance from the mirror as it looks like I am on the opposite side of the mirror. So the farther away I am from a mirror, it looks like I'm farther away on the other side of the mirror. And when we're talking about geometry, this would be like your mirror. And if I'm looking at the mirror and I'm this far away at that point, I'm going to be the same distance on the other side as well. Same thing with down here. That's just a little bit of a distance. Right there is the same. That's our longest one, and it's our longest one on the other side too. So those are all the same distances away from our line of reflection. A translation, which is the same thing as just sliding our image. That's what we had up top right here. It moves all of the points of the original figure the exact same distance in the same direction. So if I were to draw lines from K to P, from L to Q, and from J to M, all of those lines would be exactly the same distance. Next one, a rotation or a turn is a transformation around a fixed point called the center of rotation. Our center of rotation doesn't have to be on the image, but I think about this like a clock. If I have a clock, and I know that's not a great picture there, but my second hand, if the point on the end of that second hand will stay an equal distance around as it's going around the clock. So same thing here. This T and this Y are the same distance away from that point, but so is the X with the S. It stays the same distance, and R and W are also the same distance. Rigid transformation. So right here we basically have three different definitions that are all the exact same. A rigid transformation, another way we call that is a congruence transformation, or an isometry. Okay, so this one, this, and this, those are all three definitions that you you'll see those vocab words around, but they all have the same definition. Basically what that means is the position may differ from the pre-image, but the two figures remain congruent. Basically, it doesn't get any bigger or smaller. So some examples of isometries would be, let's just do a rectangle. So I know that's not a perfect rectangle, but this would potentially be a rotation of that rectangle, right? Or I could slide it. So maybe I move it over here. Or our last one was the reflection, and a reflection is kind of tough to draw, but maybe I'll draw a different figure. So if I'm reflecting this guy, it might look like that, and this would be our line of reflection. One thing that's not an isometry is what we're going to eventually call a dilation, which would be something like this. If I have a square, making it bigger like this, that would not be in isometry because it's changed size. That's basically what this is saying. You can't change the size or the shape. So these are some problems you might see on Alex. I'm going to go really quickly through them. This first one, this would be my line of reflection. So that would be a reflection. This one here, it's just sliding down. So that would be a translation. This would be a rotation because we're taking this L shape, it's like a backwards L, and we're basically tipping it over this way. And then this one, I have another line of reflection going right down the middle. So that one would also be a reflection. Now it says in each part, the solid figure, we're going to reflect it. So basically I need to draw a line of reflection here. There's not a line of reflection that will flip this one over. It might look like this could be the line of reflection, but this shape would actually end up down here instead of right there. And it doesn't really flip over the line. It's not really, it doesn't really flip over the line very well. This is not possible. So let me erase that fake line of reflection. Let's move on to the next one. On this one, you can definitely see that it is flipping over this line of reflection right here. And that line of reflection is actually at, I'm going to do a better job of drawing it here. Okay, it's about there at that line. That's my line of reflection. If I gave this line a name, it would be, since it's crossing the y-axis at -1 and it's horizontal, it would be a y equals -1 equation. Again, if it was this as the line of reflection like that right there, it would be an x equals -8 equation because it goes through the x-axis at -8. So this is just a y equals -1 equation, and it is a reflection. What is the line of reflection for the following figures? Oh no, this one it is giving us the line of reflection. It's just asking us to reflect it. So what I always do is I mark up my points like that, and I count how far it is away from the line. So if I'm starting here at the bottom one, it's 1, 2, and then it gets to the line. So I should go 1, 2, it'll be right there. This one is 1, 2, 3, 4 to the line. So 1, 2, 3, 4 right there. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4. Now, it's probably not a good idea to draw all those dots on your paper. I just tap my pen and it makes a pretty big dot. But if I connect my big dots where I ended, it'll look something like that. Okay, next one. Same thing except we're going this way. So 1, 2, 1, 2, it'll be right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right there. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right there. And 1, 2, 3, 4. 1, 2, 3, 4. Right there. All right, let's draw these out. There we go. Write the rule and draw the reflection. So the reflection here is pretty easy to draw. I'm just going to go quickly with this one though. So it should be, oh, we're going across the x-axis. I'm sorry, I was going across the y-axis. So the x-axis would be here. Oops. Right there. And lastly, it'd be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right there. Something like that. And then it wants us to give a rule for it, but I think I'm going to wait and do the rules down in the bottom. Okay, for this one, we're going across the y-axis. It's pretty similar. Should be right there. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Something like that. Like that. And like that. Okay, there's my reflection. And then last one. Okay, so now it's saying it's reflected over the line y equals x. First, maybe we should talk about what that means, the y equals x up there. And a line that's y equals x means all of your y values should equal your x values. And there's only a handful of points that you can draw on here that the y coordinate equals the x coordinate. For example, 0, 0, 1, 1, 2, 2, 3, 3, and you get the drift here. I'm going to try to make a perfect line here. Something like that would be my line of reflection. Okay, so that's what it's reflecting over. I also want to point out what this means. If I just have a y by itself, that means that's the original image. So this would be like the problem that I gave you, and this would be you reflecting it. We call these little things on the variables primes. So this would be like y, and that would be y prime, meaning that's like the second generation. If I wanted the third generation, it would be y double prime, or y triple prime. Oops, that was almost 4. Or quadruple prime would be like the fifth generation. So again, that y prime just means it's the second generation of it. Now let's talk about what this is saying over here. It says, well, first of all, this is how we write rules, like this. This arrow means like changes to. So we're changing this point, x, which is really down here. We're changing it to something else, x prime. So we need to find that x prime and figure out what those coordinates are. X prime is right there. That looks like it's -6, -2. Okay, let's talk about y prime. Y prime is right here. It looks like it is 2, 6. Next one, z prime. Z prime is right there. Looks like it is -3, 5. Now, if I look at these, there's actually a pattern, and there always will be a pattern. We had -2 in front and -6 in back. Now it's -6 in front, -2 in back. Right here, there was a 6 and then a 2. We changed it to 2, 6, 5, -3, -3, 5. So going down here, we're trying to look at a rule that defines what we have up there. So for this one, all it's changing is the order of the x and the y. So this one would be a good representation because it doesn't really matter if there's negatives up there. I had some students say, well, this one has a negative and some of those have negatives, so maybe I should use that. I don't like to think about this as a negative. I like to think about it as the opposite, meaning this -2 right there didn't switch to a +2 on this side. It's still a -2. It's not changing that. It's not an opposite. So this is why this is correct, because all that it's doing is switching the x and the y around into different spots. So that's our answer for that one. I think that's actually